And I hope all of us continue to have that experience for the rest of our lives.
Yeah, and can I add, as a parent, I think it's fundamental that a lot of the stuff is taught early on. When I was growing up, we had special programs, mentally gifted minors and gifted and talented education and other things. Now they have STEM fields and things like that nature. But I honestly don't think that we teach things early enough. I think that we wait too long to teach fundamentals of mathematics and teach critical thinking. And I'm a big fan of philosophy. You write a little bit about philosophy in your writings too. I think that a basic understanding of philosophy is critical, even in grade school.
Well, I think we're all philosophers. I don't know if you need to. I don't know if you need to understand Kant or Leibniz but what I think you need to do is realize that we're all doing philosophy. I mean, I've made some statements about philosophy and physics which have gotten some philosophers upset. But the point is, what philosophy is just critical thinking, assessing knowledge, and trying to help frame good questions. And that process is something we should all be engaged in. And if you want to call it philosophy, that's fine. But it's a process that I think is really part of science and part of what we all do on an everyday level when we're trying to be rational.
Mm-hmm. I agree. So we're going to, oh, please.
No, I just wanted to say, I think young kids can appreciate, I think too often people think that young kids can't understand more advanced concepts. And I found that, if you can talk about in many ways, even modern physics to young kids. So I think the question is, are people motivated? And what makes, I guess, astronomy and particle physics so easy in that sense is that people are fascinated by the universe. And you can use that to try and get kids hooked into asking good questions. That's all I wanted to say.
Mm-hmm.
Absolutely.
I'm going to ask a couple of the questions that we're getting from the live chat. And the first one is from 0132-132. Thank you for the super chat. It said, since there's only one microstate consistent with nothing as a macro state, does it make any sense to say that nothing has an entropy of 0?
Well, actually, that may not be true. You see, once again, nothing, it depends what you mean by nothing, and you have to be very careful. For example, if, as we observe today, empty space, which many people would call nothing, has energy, then Stephen Hawking would have told us it also actually has a temperature, something called the Hawking temperature. And if it has a Hawking temperature, it has entropy. In fact, I just attended a meeting where I was speaking at my university just last weekend, where people were actually trying to calculate the entropy, not just the energy, but the entropy of the vacuum. And so the vacuum is much more complicated than it may appear on the surface. And so it need not be the case that the entropy of nothing is nothing in quantum mechanics.
And he asked me the same question. I told him almost the same thing. So thank you. Thank you, Zero. Love
good.
I pretty much parroted that, yeah.
The next one is from Red-Eyed Zaza, who says, to Dr. Krauss, what scientific discovery do you most anticipate? Love your work.
Thank you very much. The one I most anticipate is one I haven't even thought of now. That's the most exciting thing, is to have something be discovered that I never even thought of. So let me say, that's without a doubt what I hope for every day, is that that my picture of the universe will change in ways I never imagined. But in terms of discoveries that I can imagine, again, I rarely rank things hierarchically. I would love to be able to actually detect gravitational waves from the beginning of time, because as I told you, that they would tell us a lot about not just the beginning of our universe, but the existence of other possible universes. I would love to be able to, I spent much of my career trying to figure out how to detect the nature of dark matter. I would love if we detected dark matter directly in the laboratory, so we'd know what particles were the dominant stuff in the universe. I would also love to be able to identify the existence of life on other planets, that there's evidence for living processes on other planets. That may also be observable perhaps in my lifetime. Those would be amazing, just in physics. There are lots of other things I'd like to be able to discover too. But in physics and science, I think I would love to be able to know the answers to those questions. But once again, in my experience, the most exciting thing are things I hadn't anticipated at all. That's why it's fun being a scientist. After all, if you can anticipate everything, it's not that much fun.
Savage King 23 asks, Dr. Krauss, do you have a possible solution for the discrepancies in the measurement of the Hubble constant?
Yeah, I just tweeted it yesterday. I know it got a lot of press today. It was in a big New York Times story about it. It's been in other magazines and journals over the last few weeks. I'm not sure if it's much ado about nothing. I hate to keep talking about nothing, but my suspicion is that the resolution of it is what is really quite pedestrian. Observational errors. I think that's far more likely than any of the wild theoretical constructs I've heard. Far more likely. When I was growing up, two different groups measured the expansion rate of the universe. And in a set of units that doesn't really matter, as I just said in my tweet, one of them measured the value 100 plus or minus 5 or 7. Another measured 50 plus or minus 5 or 7. Well, clearly, they couldn't both be right, and clearly their estimates of errors were wrong. Now, their estimates of their statistical errors were right. Their statistical uncertainty was plus or minus 7. But in astronomy, what comes and bites you in the butt all the time is something called systematic uncertainty. Things you can't have foreseen, that this experiment was a little hotter than you thought when you made the measurements, and therefore they're skewed in a certain way. And right now we're measuring these two different ways of measuring the Hubble constant, the expansion rate of the universe. One is, I think, 67 plus or minus 2, and one is about 72 plus or minus 2. So they differ at what we would say maybe 2 sigma maybe a little bit more in the language of scientists. And so maybe they measure very different things. One measures the expansion rate of the universe at early times, and one measures the expansion rate sort of today in a more general sense. Maybe there's some maybe it does mean something fundamentally crazy is happening in our universe. But based on my experience of 50 years, 40 some odd years of being a scientist, I think it's also quite likely that we'll find that there are systematic uncertainties, and in the end, these two discrepant numbers have come together. And it's kind of funny when you think about it. When I was a young assistant professor and there was this value of 100 and value of 50, I used to say, well, clearly the answer is going to be 75, right? And what did it turn out to be? Close to 75, because what it turned out is each experiment had large systematic uncertainties, and the answer was somewhere in the middle. I wouldn't be too surprised if the answer is that the Hubble constant lies somewhere in the middle, and this concern is misplaced, but I could be wrong. But I think we before we jump to wild hypotheses, we have to rule out the simple things first. And before I'm convinced, well, if someone has a theoretical argument that's really attractive, I might begin to suspect that it's right. But nothing I've heard is attractive. It's all Baroque as a way of explaining away what I think ultimately is probably going to be an observational error. But we'll see.
Would that be something similar? Would that be something similar to maybe systematic errors in the fine structure constant, when we look one way and it appears to be one value, and we look the other way and it appears to be a different value?
Yeah, though I believe that people have now demonstrated that was an observation, that difference was in fact due to a systematic uncertainty of measurement. So people have now demonstrated that's a great example, because for a while people were saying, look, the constants of nature are different in different directions. Wow, the laws of physics are crazy. We have to change everything we understand. And that might have been true, but it's also possible that the systematic uncertainties were such that what they were seeing was not really what they thought they were seeing. And it's often the case. People should be skeptical. When you read in the newspaper about some discovery that appears to disagree with things that we've measured otherwise, it seems to be wild and crazy, you should realize that most such discoveries go away. Same for theories. And so take every such report in a newspaper with a grain of salt, or maybe a pound of salt.
Does that mean that you expect to figure out the huge discrepancy between vacuum energy density and 0-point energy, like 120 some odd magnitudes difference? Because I think that'd be an amazing thing to try to reconcile. Because that's huge.
Well, I've tried. I've spent a lot of my time trying to understand why the energy of the vacuum is what it is and why it's so small. I've even written papers on it that explain it. Those papers are probably wrong. I spend a lot of my time thinking about it.
That's half the fun, being wrong and then figuring out.
It's true. But maybe one of them will be right, but it's a hard problem, and it would be great to resolve it. But it's a hard problem.
One of our really good friends who has a science channel and debunking the things like we were talking about earlier, the flat Earth and just a narrative that doesn't comport with reality is Red's Rhetoric, and he's actually on the call with us now, and he has a question that he wanted to ask you. Reds, are you here?
He's asking it very quietly.
Yeah, Reds. You might be
muted, I can't
Reds.
Impersonate Reds. I'm not good at doing a Red's Rhetoric imitation.
Okay, well, while we figure out where, he was here. Rez, we can't hear you. I'm going to go to the next. Oh, well, maybe send him a message, and I'll go to the next question while we wait. So the next question here is Pragmatic Culture wanted to know if you could be more specific.
Well,
by what? Oh, there we go. Reds.
There we go. I had to refresh the
page.
Yeah, for a moment there, I was like, wait a minute, what? It says I'm not muted. Whatever. I don't know this platform that you guys use. Hi, Dr. Krauss. How's it going?
Pretty good, thanks. How are you?
I'm doing well. Anyway, got a few questions if you don't mind. I'm going to start off with...
If they don't mind, I don't mind.
Okay. Well, it's going to be a childish question, so let me start off with the first one. Did you cry when you had to say goodbye to the Opportunity rover like I did?
Oh yeah, I wrote about it. I tweeted about how I didn't cry, but I was very sad. It was a very emotional moment because as I've written before, I'm far more attached to the rovers than I would be to any astronauts. The rovers are much more romantic objects for me than any astronaut going to Mars. I don't know why people are so excited by sending astronauts to Mars. The rovers, they're all by themselves. But they live for 15 years alone without companionship going on the planet. It's just it's so romantic.
It wasn't supposed to. So how long was his life?
I know, and that's what's great about them. And that's what's great about them. And as I've often said, those rovers were sent to Mars for the cost of making a movie about sending Matt Damon to Mars.
Yeah.
And that's the difference between sending rovers and humans.
Well, and in all fairness, they're actually fixing that with all new rovers because now Curiosity has the ability to sing Happy Birthday to itself. So that's at least a step in the right direction.
Well, and that's what's great. As we develop new kind of robotics and artificial intelligence, the machines that we'll be able to send into space will become ever more sophisticated, and the need to send humans to do the experiments will become less and less significant. The only reason to send humans into space is a sense of adventure. I think the best. There's no doubt that the best science we do doesn't involve humans in space.
Yeah. Well, this kind of leads me to.
I got a lot of flack from my friend, say Neil deGrasse Tyson about that. But anyway, go on.
Well, speaking of Neil deGrasse Tyson, Neil deGrasse Tyson is very famous for the stuff that I do, which is debunking flat Earth, because I guess I just have nothing better to do with my time. But Neil deGrasse Tyson once famously said, the Earth isn't fucking flat. And I think this should be a thing that all famous smart people say. So with your permission, Dr. Krauss, since you are a famous smart person, can we get a soundbite?
Well, I like to let Neil say his stuff and me say my stuff. The Earth isn't flat. And the most important thing is, as Neil said about something else, and as I've said about something else, it isn't flat whether or not you believe it's flat. The Earth doesn't care what you believe. The universe doesn't care what you believe. And the Earth isn't flat, like it or not. Get over it.
And it's not 6,000 years old either.
Yeah. Yep. And my last question.
Get over it.
Yep. And my last question. And it's going, back to how we should be doing compared to how things are actually doing. Do you think it is better for us to blast telescopes to the L2 Lagrange point, or should we reinvest that money on ground-based telescopes since their capabilities are becoming, so great, especially with stuff like adaptive optics?
Why not?
Well, look, I think I think you can have both. I mean, you can have both, but you're right. One has to make choices at some